My name is Alicia Pastor, and today I'm going to be talking about Crossflow cooling towers. Now, the last cooling tower presentation focused on why cooling towers are used and how they're classified. So I'm going to focus more on the actual procedures and what's going on inside of them. At the end, I will compare cross-flow and counterflow towers, but all the sections I'm about to talk about apply to both types. I'd like to start by reviewing some basic thermo concepts. The information on this slide will not be covered in the quiz. There are two kinds of heat energy. Sensible heat causes a change in temperature at a constant phase and is represented by the orange lines and arrows in the figures on the slide. Latent heat causes a phase change at a constant temperature and it's represented by the horizontal green lines and the arrows shown on the slide. It should be noted that the latent heat energy required for a phase change is much larger than the sensible heat that's needed to change the temperature of a substance. All cooling towers operate under the principle of evaporative cooling, which I will illustrate below. Particles 1, 2, and 3 represent hot water. If particle 1 is to evaporate, it needs to absorb sensible heat from the surrounding water particles to gain enough energy for latent heat transfer. In other words, it needs to gain enough energy to change phases from liquid to gas. Because particles 2 and 3 had to give up sensible heat for the evaporation process, they experience a drop in temperature while remaining in the liquid phase. As a result, particle 1 now represents hot water vapor, and particles 2 and 3 represent cooled liquid water. The figure on the left shows the components of a cross-flow cooling tower. The figure on the right is a process diagram that shows the path of the air and the water. The air enters through the air louvers, which have a slope shape to prevent any debris or animals from entering the tower. The hot water enters through the hot water distribution deck, otherwise known as the hot water basin. At the bottom of the hot water basin are gravity-fed nozzles that are responsible for evenly distributing the water across the fill material. The fill material is the point at which the water and the air come into contact, which is why it's colored purple. It's the heat exchanger surface where the evaporative cooling takes place. After the evaporative cooling has taken place, the cooled water falls into the cold water basin and is sent back to the chiller or condenser to be reused. The water vapor that was formed mixes with the ambient air and heats it up. This hot, saturated air then passes through the drift eliminators. The drift eliminators force the air through a convoluted path so that it can catch water droplets that the air may have picked up and prevent them from escaping. After passing through the drift eliminators, the air enters the plenum area and is then pushed up and out of the tower by the fan and released into the atmosphere. Besides water that is lost from evaporation, cooling towers lose water due to drift, blowdown, and leaks within the piping system. The figure on the right is showing a counterflow tower, but crossflow and counterflow cooling towers experience the same sources of water loss. So this figure is being used to illustrate the water loss points. Drift is water droplets that are picked up by the air as it moves through the tower, and the drift eliminators are installed to pick up these droplets and minimize water loss. Blowdown water is water that's drained from the cold water basin to remove impurities like dissolved solids that are left behind when water is evaporated. System leaks are self-explanatory and can happen at any point in the process. Makeup water is pumped into the collection basin as needed to compensate for the losses from evaporation, drift, blowdown, and leaks. To minimize the costs associated with using makeup water, operators want to recycle the processed water as much as possible. Most cooling towers can cycle their process water 2 to 4 times, but some can be reused up to 8 times. When the water evaporates, it leaves behind dissolved solids. When the concentration of dissolved solids in the water is too high, the solids deposit themselves onto surfaces in the cooling tower. This causes scaling, fouling, and corrosion. This is why there's a limit to how many times the water can be recycled. When these minerals deposit onto heat transfer surfaces, they act as insulators and lower the heat transfer rate and the overall cooling efficiency of the tower. The concentration of dissolved solids in the water is determined by measuring the electrical conductivity of the water. When the conductivity reaches a certain threshold, the water must be drained. This is the blowdown water. Draining blowdown water is effective for controlling scale and corrosion, but this does not address the problem of biological growth. The most dangerous kind of biological growth is Legionella. Legionella is present in all cooling tower systems because towers naturally create an ideal environment for Legionella to live and grow. Small concentrations of Legionella are harmless, but exposure to Legionella via inhalation can lead to Legionnaire's disease, which is a form of pneumonia that can be fatal. Legionella bacteria escapes from the cooling tower through drift particles, which is another reason why drift eliminators are an important component of the cooling tower. The primary defense against Legionella growth is chemical treatments in the process water, but it is not possible to completely eliminate Legionella in a cooling tower system. There are other ways to prevent ideal growth conditions for Legionella. First of all, it is important to keep water temperatures above 122 degrees Fahrenheit and below 68 degrees Fahrenheit, designing the system to minimize opportunities for stagnant water, replacing corroded components, and ensuring that high-efficiency drift eliminators are being used. It is the responsibility of the cooling tower's maintenance and facility services to monitor and control Legionella concentrations in the water systems to ensure the safety of public health. The main difference between cross and counterflow cooling towers is the direction of the air relative to the water. But now I'm going to discuss the practical differences between the two when they're being selected for operation. The operational considerations I'll be discussing are space requirements, maintenance access, water distribution methods, low flow operation, and cold weather operation. In crossflow cooling towers, air enters on two sides of the tower. Counterflow towers, on the other hand, have air entering from all four sides of the tower to the bottom of the tower. For heat loads of less than 750 tons, crossflow towers need significantly more space than counterflow towers. This makes counterflow towers an ideal selection if they're being used in a densely populated area. The main advantage of crossflow towers over counterflow is the ability to access them for maintenance access. This is mainly due to the plenum area for each of the towers. As you can see, crossflow towers have a large plenum area in the center of the tower. There's full door access, which you can see right here, and maintenance workers can stand up completely and reach all of the components of the tower. They can also easily climb a ladder and reach the fan and water distribution decks of the crossflow tower. On the other hand, counterflow towers have a very small plenum area and have their components stacked on one another. Again, this makes them a more compact cooling tower design, but makes it much more difficult and time-consuming to access if repairs or maintenance need to be done. Another important distinction between the two is the way that water is distributed across the fill material. In crossflow towers, water is fed through the nozzles and pushed through by gravity. This ensures that the water is spread out evenly and that the fill material is evenly wetted. Counterflow towers, on the other hand, have to pump water through branch arms and then through pressurized nozzles. This means that the pumps for counterflow towers need much more power, and any issues with power or pressure supply can result in a decrease in the efficiency of the cooling tower overall. In the event that the tower has to operate under low flow conditions, the pressure drop in a crossflow tower will be even because the nozzles rely on gravity. In counterflow towers, on the other hand, if there is a loss of energy, water channeling can start to happen. Crossflow towers' performance can be predicted up with as little as 30% of their design flow. Counterflow towers, on the other hand, become unpredictable at about 70% of their design flow. The final consideration is the way the towers perform under cold or freezing conditions. The configuration of crossflow keeps the hot water on the perimeter of the tower and keeps the colder tower on the interior. This discourages freezing throughout the tower. Counterflow towers, on the other hand, can experience icing if water channeling is occurring. And there are also opportunities for ice accumulation to happen within the air louvers that can go undetected by maintenance or facilities operations. In conclusion, crossflow towers are cheaper and easier to maintain and hold up better in low flow or cold weather conditions. However, it ultimately depends on the intended use of the cooling tower.